What's up guys, your boy's back, XX Sonicata XX, back with another FRQ Set 5 video, part 3 of the 5 upload day. Now, this problem is unlike the others in that there are no numbers involved. Actually, there's 1 and 2. 2 numbers involved, but whatever. We don't actually use them much. Anyway, basically, there is a ring. Ring instantly tells us that the moment of inertia is mr squared. Okay. So it's initially sliding on a frictionless surface at a constant velocity, linear velocity, VO, or V0. And at time equals 0, it experiences friction, so it starts to slide and roll, meaning there's both linear and angular velocity. And after it crosses the distance L, there is only angular velocity. So part A, we're supposed to express all answers in terms of m, r, VO, and fundamental constants, such as mu, g, whatever. Okay, anyway, part A. Starting from Newton's second law, in either translational or rotational form, derive a differential equation that we use to solve for linear velocity and angular velocity. Sorry, it's curved. Okay, let us start now. Part A, part 1. So it says use Newton's second law, either rotational or translational. So we're going to start with linear velocity. And since it's linear, we better use the translational. Newton's second law, which is net force times mass times acceleration. Or net force equals mass times acceleration. And the only force acting on the ball at time equals t at all is f of k right here. And it will be negative because it is pushing against the ring. Negative f of k equals ma. F of k equals mu times fn, and f of n equals mg. So we end up with mu mg equals ma. Since there's m on both sides, we can cross that out. And we end up getting mu g, negative mu g, equals a. Now they're asking for a differential equation, so we better have a derivative in there. So we know that the derivative of velocity equals acceleration, so we can put negative mu g equals dv over dt, the change in v or the change in time. And that is our differential equation. Now, part 2. They're asking for angular velocity, so we'll use rotational Newton's second law. Net torque equals moment of inertia times angular acceleration. Net torque equals net force times axis of rotation, which in this case is equal to the radius. Your moment of inertia is mr squared, and then alpha. We can cross out this r and this second r, so we get net force equals mr alpha. Like before, the only force acting against the ring is f of k equals mr alpha. Like before, f of k will equal mu mg equals mr alpha. Cross out m's again, we get mg equals r alpha, and we move r to the other side to isolate for alpha. Now, like how the derivative of velocity is acceleration, the derivative of angular velocity, or omega, is equal to angular acceleration, or alpha. So we end up getting mg over r equals d omega over dt. Pretty easy for part A. Now, part B asks, derive the instructions for the magnitude of the following as the ring is sliding and rotating. Find the velocity and the angular velocity. But this time, we're supposed to just solve for them outright, not solve them via a differential equation. And that's pretty easy. All I have to do is copy this, dv over dt equals ug. How do you turn a derivative into, or how do you cancel out a derivative basically? You integrate. What do you integrate from? Since we need v0, the initial velocity as its answer, we'll make a bound of 0 beginning bounds of 0, and end bounds of t because we're trying to find it as a function of time. Now, through the fundamental theorem of calculus, if you don't know what that is, you should probably search it up because it will be very useful. Through the fundamental theorem of calculus, this will equal v of t minus v initial equals the integral of a constant. You just add t into it. Oh, I forgot to add dt and dt here. This crosses out. So negative mu g times t. Isolate for v of t, and we get negative mu gt plus vo. Pretty simple. Now for part 2. Part 2, we do the same thing. D omega and dt equals mu g over r dt. Take the derivative of both sides again. I got a little ahead of myself. Okay. And I'm getting same thing as fundamental theorem of calculus. W of t or omega t minus omega 0 equals, this is whole thing is a constant, so we just plop another t into it. 0t mu g r t. Now, I see the problem. Initially, there is a v0, but it is not rotating. Therefore, there is no omega 0 initial omega. Therefore, we can just simply cross this out, and we end up getting omega t equals mu gt over r. Okay, part C. Derive an expression for the time it takes for the ring to travel distance L. So we have to find the time, and voila, there's the time here. We can isolate for. But we still have one unknown here, v of t. But after a distance of L, which is where we're trying to find our time from t equals 0 to the end, at this point, there is no more sliding, just rotating. Therefore, there is no more linear velocity. There is just angular velocity. And therefore, we can use v equals r omega to find our v. So we have v of t equals negative mu gt plus vo. Isolate or substitute v for r omega of t equals negative mu gt plus v0. And as we found out in part B, part 2, omega t equals mu gt over r. We can just plug that right in. Mu gt over r equals negative mu gt plus vo. We can cross out the r's here. Okay. Next, we have to isolate for mgt. Oh, there's actually 2 of them here. Whoa. Okay. So we can bring both t's to one side by adding this to both sides. Mu gt plus mu gt equals vo. Combined like terms, this becomes 2 mu gt equals vo. And we move all this to the other side by dividing by both sides, and we get t equals vo over 2 mu g. That is solving for time. We have everything we need in the answer. Okay. Part D. Part D asks, derive an expression for the magnitude of velocity of the ring immediately after it has traveled the distance L. So, part D. We have to find the velocity after it travels the distance L. So we'll use v of t equals negative mu gt plus vo. But how do you know what t is after it travels distance L? Well, from part C. Because part C, that makes you find the time it takes for v to cross the entirety of distance L. So using that amount of time, we can find the velocity after it has crossed L. So v of t equals mu g. T, we can substitute in what we had in part C, vo over 2 mg, or 2 mu g. Have I saying m the whole time? If so, I'm sorry. Plus vo. Okay, we can cross out mu, we can cross out g. end up getting Vt equals Vo over 2 plus Vo. Well, it's actually negative. Whoa, forgot the negative here. Combine like terms, Vo over 2 plus Vo just equals Vo over 2. And that is our velocity after we cross the distance L, half of our initial velocity. Lastly, part E. Derive an expression for the distance L. We can actually do this multiple ways because we have many different formulas that have velocity, acceleration, time, anything you really want. So I will use the position formula. Delta x equals vi, or Vo in this case, t, plus 1/2 at squared. Okay. So our distance that we need to find is L. VOT, we can't leave that alone. We know what t is from part C, which is VO over 2 mu g plus 1/2 a. What is a? In part A, we found out that a equals negative mu g. We'll plug that right in. Negative mu g. T squared. We'll plug in VO over 2 mu g squared. So now we have to simplify this in order to get our answer. VO, we can multiply that over VO squared over 2 mu g plus negative mu g over 2. Multiply those two together. And we'll distribute this squared over VO squared over 4 mu squared g squared. Okay. Nothing's happening here so far. We can leave this alone. Plus, we can cross out these two squares for this. And then we can combine the denominators and the numerators together to get, well, it's a negative here, so it's actually minus VO squared over 8 mu g. 2 times 4 equals 8, and we have mu g left over at the denominator. So, in order to get the denominators similar, we multiply the top and bottom of VO squared over 2mg by 4. And we end up getting L equals 4 VO squared over 2 times 4 is 8 mu g minus VO squared over 8 mu g. 4 VO squared minus VO squared equals 3 VO squared over 8 mu g. And that is our distance L. Okay, that's all the parts. Thank you so much for joining. This is your boy XX Silent Killer XX. I'll see you in the next one. Peace.